All right, people, today we are going to be talking. Oh, wait, that's the wrong bone. All right, here we go. Hey, we're going to be talking about the skeletal system. We're learning all about the human skeleton. If you're someone who's taking avid notes here, you want to start jotting down that essential question. If you're somebody not an avid, but you still want some nice study skills, you want to be able to answer that question by the end of this presentation, which is, how does this system, specifically the skeletal system, how is it going to support, protect, and keep humans functional? So you might want to write that down. Maybe you're already writing it in the summary section because you know you're going to try to answer that question by the end of this presentation. So let's get into it. We're going to split this into three parts, really. We're going to look at how bones are organized and like their physiology, so what they're doing. This is going to be a lot of vocab about how we classify bones, how we're going to remember bones, how we're going to like organize them based on maybe some similar features. Next, we're going to look at the skeletal system on the microscopic level. So we're looking at cells, bone cells, blood cells, tissues, minerals, how, like, what's going on in our skeletal system on a level that we can't even see. Finally, everybody's favorite, we're going to talk about growth and repair. So when you're a kid, how do you reach an adult size, right? How does that happen with your skeletal system? And then, hopefully not, but what happens if we break a bone? So if you've ever had an x-ray, you go in, you see something that shouldn't be there on the x-ray. What's going on in our body so that way we can fix that with just a cast sometimes, right? So that's how we're going to look at all this stuff today. And here's kind of my spiel about what we're looking at. Hey, bones, when we think about them, a lot of people are like, "Ooh, it's scary, it's death, all about death." But really, bones are alive. They are working for us all the time to provide support, movement, protection, and they're also working to maintain balance in our body or maintain homeostasis. Your goal at the end of this is to understand how our bones play a role in our mineral balance, how we grow, our overall function, how we repair things, how it connects to maybe some other systems that we're going to learn about, and, just appreciate what's going on inside of us with these bones. Maybe you might realize, hey, that's not so spooky after all. It's not that scary. All right, let's get into it. In our textbook, we're going to see a lot of this in activities. We're going to maybe be asked to organize bones a certain way. So let's see how the scientists do it. When we are looking at a skeleton or we are talking about a skeleton in this class, scientists and doctors, medical professionals, anybody who works with the human body can sometimes refer to the skeletal system in two parts, the axial skeleton and the appendicular skeleton. If you are seeing these diagrams here in yellow, the appendicular skeleton, you can see it's like, I think, appendages, right? It's like our arms, our legs. It's nothing really in the center of our body because that's reserved for the axial skeleton. I think about the word axis, and like the earth is on an axis, right, that goes through the middle of the earth. So I think about the axis as like the middle of our body. In that middle part, we're talking about all bones and cartilage that support and protect the organs of our head, neck, and trunk. So like everything in here, all the organs like in our torso area, all the way like through our hips. And then when I think about the appendages or the appendicular skeleton, that's all the bones of our upper and lower limbs, so our arms and legs, and that's going to include the clavicle, our scapula, and our hip bones. So if you are thinking that it's easier to look at this right now, right, and you're seeing the yellow bones, the appendicular skeleton on this image, the orange one is going to talk about the axial bones. Another way scientists are going to refer to bones is by their shape, and they're going to classify them into like five-ish areas. Long bones are long. They're longer than they are wide. This is kind of like your classic bone that you think of when people think of a bone, right? An example would be our arm and leg bones. So those ends are large enough for like tendon and ligament connections or attachment points. So we can like move our bones certain ways and use our muscles to move those. Another classification, we're going to talk about irregular bones. These, they're irregular, right? They don't really fit into any other category. They're kind of a funky shape sometimes, or a variety of shape. A lot of these are connected to several other bones. So if you think of like our vertebrae, they are examples, or spine, right? They're examples of like irregular bones. They connect to a lot of other things. And also like our facial bones are very irregularly shaped. It's hard to classify them as something else. Short bones, on the other hand, are a little easier to classify. They are short. They're equal in length and wrist, or length and width. Some example would be like bones in your wrist, bones in your ankles. I like to think of these as like they're very square looking sometimes. And this includes like a special sesamoid bone. Some people consider this like its own separate thing. Some people say it's a short bone. It's just a special short bone. And it is shaped like a sesame seed. So if you've never seen a sesame seed before, right, that sesamoid bone is going to look like kind of like that, like a little teardrop, like a little seed. And an example of this would be our patella or our kneecap. And finally, we got flat bones. Those bones are flat. They're very plate-like. They have broad surfaces. So like our skull bones, right? Like the top of our head are going to be considered flat bones. Other examples are our ribs, our scapula, or our like your shoulder blades. And we'll look at all of the classifications on this next slide. We've got how we categorize all of them, and you are going to do like a little activity at some point where you're going to have to classify these bones. So when you're seeing something like this, I'm not going to read all of them out, but if you're looking back on your activity and you're like, oh goodness, I cannot figure out, should the fingers be categorized as long bones? That's where you want to come back to this slide and reference this if you are getting stuck. And we're going to take like a deep dive on the physiology of long bones. So like what's exactly going on in there? We're using long bones as an example because they are kind of the perfect bone to look at. They've got all the parts we want to identify so we can kind of understand what's going on there. So first section, if we're looking at like, here we've got the femur, right, which is an example of a long bone. That whole middle section. So if we're looking at this entire middle, right, we're seeing like this whole part of the bone, really. That whole middle part is called the diaphysis. It's that middle section. It's like the shaft of the bone. It's mostly made of compact bone. So it's very dense, which is nice to keep it nice and strong. It's covered in a thing called the periosteum, which is very dense. It's like a connective tissue, and we want it to be dense so that way it's hard to break, right? If you were to look inside of it, right, all the way in here, it's very hollow on this inside. That's called the medullary cavity. As kids, we have red bone marrow inside. As adults, we really have yellow, mostly yellow bone marrow. And that inner lining is called the endosteum. We'll talk a little bit about that later as well. But really the big idea here is this middle section's got that nice hollow spot in it, and there's a lot going on in there to help us exist. If we're looking at, we can kind of see like the ends of our bone, of our long bone here. The ends are called the epiphyses. And right before we get to that section, there's a little part right here that joins the middle part to those end parts. So it's really just where the diaphysis joins the epiphyses. In children, so anybody who is not done growing yet, those are called growth plates, and we'll take a closer look at that as well. And then as an adult, they're no longer growing. So they're just there. They're a little bit of a line, I guess, to say where our growth plates used to be growing. So when we're just talking about the ends here, the ends of the bone, the epiphysis, so that's just really like this whole end of the bone, also on the other side, right? This part's gonna have spongy bone on the inside and compact bone on the outside. We'll take a look at exactly what that looks like. This is where we can form joints with other bones. So it's like really what's giving us like a lot of movement, what makes it possible to like lift things, run smoothly. And if we were to look even more closely at it, we would see that like the ends are often coated in a special type of cartilage called hyaline cartilage. So on the ends there, we've got this really smooth cartilage. If that cartilage were to wear away, any joint movement would be not very smooth. It would also be pretty painful. So you can thank your hyaline cartilage for making sure your runs don't hurt as much as they could. Because let's be real, running is hard. Looking a little bit at the difference between that spongy bone and compact bone, most parts of that spongy bone, you can tell right away, there's like a lot of gaps in there, right? If you were to compare it to a sponge, I think it'd be really similar. Those gaps keep the bones nice and light so it doesn't like hurt to lug our bodies around all the time. It also allows a lot of space so nutrients can get through this area easily. In adults, we have red bone marrow in this spongy bone. So that's like the last spot where our red bone marrow is. This is where blood cells are made. And if you are looking at that compact bone, right, it's what keeps our bones super durable. Blood vessels and nerve fibers can like travel through a central canal in compact bone. And we want those nerve cells and blood cells to get everywhere so we can get nutrients and send signals when something's out of whack. And this is really formed by osteocytes, which is a special type of bone cell that we're going to look at. And they're clustering concentrically around the central canal. So if concentrically is a new word for you, right? We've got it defined over here. That's supposed to be a star, but I'm struggling. Really, I think about like cone or center, right? It's a series of circles or rings that's arranged concentrically. It means they all have the same center, right? So if I'm teaching a class, right, and everybody's going to arrange themselves around me, it means everyone's going to sit where I'm at the center, right? Or if you're going to get in a team huddle, the captain's in the middle, you're all going to be around them. Hey, they're all having the same center. To truly understand the skeletal system, we need to take a look kind of deeper what's going on the microscopic level. So the level that's so small, we need a microscope to really like see what's happening there. Things in this section we're going to try to take time to understand are the cells and the tissues of bones. So like, what are those cells doing? What's the tissue's function? What's up with those guys? All right, so to truly understand this, we're going to look at some like tissues and cells here. This first one, the skeletal extracellular matrix, we're going to classify that as a tissue. It's made up of collagen and inorganic salts, really calcium and phosphorus here. And if I'm somebody who's like taking good notes, right? The calcium, something we've already talked about in our last unit. That's going to be a big one in terms of like maintaining homeostasis in the body. So if you're writing in your notes, you maybe put a little like note here off in the margins. You could write something about homeostasis. Ooh. Homeostasis, like connection, is what I would make a note of. Is this calcium right here. So if you're somebody, you're trying to make some connections to other things, that's like our previous unit, right? One of the cells we're going to look at is osteocytes. These are mature bone cells. They maintain all the bone tissue. So we'll take a look at their like specialized role really. But that's something that we're going to see a lot of. They also play an important role in like balancing the minerals in our body. Osteoblasts are cells that are bone building. I like to remember this one. Hey, blasts starts with B right here, and we're talking about bone building, which also starts with a B. So they're going to build bone cells. They secrete extracellular matrix. Once they're done with that, they turn into osteocytes. But this is how we get like new bone, how we repair broken bones. And then finally, we're also going to look at a bone cell called osteoclasts. If we look at the clast part that starts with a C, right, I remember that this cell crushes bone. So it's digesting the extracellular matrix, and we're going to take a look at why it does that. But just for me, I think blasts build bone, clasts crush bone. So one question like I really had when I was learning this is, okay, this seems counterproductive. Why do we need cells to crush bone and build bone? Really, there's two answers for this. We need some bone builders for grow and repair. And during that growth and repair process, sometimes we need bone crushing cells to get rid of the imperfections. We also need to increase the size of that medullary cavity, which if we remember back, that's like in a long bone, right? That's the hollow part in the middle, right? So if we're looking at a femur, oh goodness, if we're looking at a femur here, oh my gosh, right, that's going to be the part right in the middle, right? That medullary cavity is right in the middle. It's that hollow part of the bone. The second reason we need these bone building cells and bone crushing cells is to maintain calcium levels in our blood. So we know that calcium is needed for many functions of the body. We know that like for our muscles to contract and move around, we need calcium to help us out with that. For nerve cell function, we need calcium to play a role in sending signals. It also helps our blood cells create clots if you get hurt. So calcium is a really important nutrient that we need all the time just for basic functions. So if we have a lot of calcium in our diet, we've eaten a lot of calcium, so we have an increase in calcium in the body, osteoblasts are going to build bone with that calcium to store it there. You've probably heard people talking about, hey, you need calcium in your diet for strong bones. You can get that through lots of different foods. People say that because if you don't have enough calcium in your bones, they're not going to get built up really nice and strong from those osteoblasts. If we don't have enough calcium, so like you need calcium to do some basic functions, there's none in your blood right now, those osteoclasts are going to break down the extracellular matrix. So they're breaking the bone itself to release calcium into the bloodstream. So if I'm making a note of this, right, this is like that big thing, hey, extra calcium, this is what's going to happen. And then also if we don't have enough, main idea here for me is like these calcium levels. What's going to happen when we have too much calcium? What's happening when we don't have enough? And if we dive a little deeper on some of the storage of inorganic salts, specifically, we're going to talk about those calcium salts. The extracellular matrix of our bone has a lot of calcium salts, unless you've had a calcium deficiency half your life. So it's storing calcium phosphate in our bones. We looked at this a little bit, right? Those low levels of calcium in our blood are going to stimulate the parathyroid hormone. So osteoclasts are going to break down that bone tissue, which is going to release calcium salts into our blood. Hey, we can use that. That's good for us to use. If we're going the opposite level, there's high levels of calcium in the blood already. That's going to inhibit osteoclast activity. So the osteoclasts are going to chill out. A different hormone, calcitonin, is telling osteoblasts, hey, it's time to form that bone tissue. So take that calcium and put it into the bones. So here I like to think, oh, calcitonin sounds like calcium, right? It's going to tell bones, it's going to tell our cells store that calcium in the extracellular matrix. So I think like calcitonin is going to be extra calcium getting stored in those bones. All right, so we've seen a diagram that kind of looks like this in our homeostasis unit. But now that we've got like a little more knowledge, maybe this makes more sense to us. So if we look at maybe what's happening over here, we have low levels of calcium in the blood. We can see that this parathyroid gland, which there's 4 of them, hey, that's going to tell us, ooh, calcium's low. Get those osteoclasts to crush up some of this bone and release that calcium back into the bloodstream. The other thing this hormone does is it tells the kidney to reabsorb some of the calcium from the urine. So don't get rid of that calcium in urine. Take that calcium back up into the blood. If we have any calcium in our diet, the small intestine is going to take that calcium and absorb it into the bloodstream, so we've got lots of calcium to use. So on the opposite end there, right, we've got a lot of calcium in our blood. If there's a lot of calcium, we're going to get a signal to the thyroid, which is this like gland sitting around here, and that thyroid is going to release calcitonin, right, that hormone that says, oh, we have a lot of extra calcium. Let's make sure we can put that into the bones, right? Store it there so in case we need it later, we can use it. So that calcitonin is going to make sure calcium in the blood gets built back into the bone with those osteoblasts. So I'm going to say it's built into bone. That's like a note you want to make on your notes as well. Finally, we're going to talk about growth and repair, kind of everybody's favorite. What happens like for us to develop into adults? What happens if something happens? What happens if we break an arm? How does our body know how to fix that? And so the fancy word for formation of bone or like growing of bone is called ossification. So fun new vocab word, ossification. It's going to mean, hey, we're growing that bone, we're forming it. So when we look at a fetus or somebody that's not born yet, prenatal, at about 8 weeks after conception, bone is starting to form. So there's really 2 ways that this can happen. Some bone is going to start originating between layers of connective tissue, and we'll look at an example of that too. So it's like intramembranous, so it's originating in between different layers of this connective tissue. And we're also going to look at a type of bone that forms because there's already cartilage there, special cartilage, and it's going to get replaced by bone tissue. And how is it getting replaced or built? We already know. We know it's those osteoblasts, those bone builders. They're forming a bony matrix around themselves and that cartilage. So we'll take a look at what that kind of looks like. So if you're looking at, here's like a slide or some sort of ultrasound of a fetus. If we're looking at the top here, we can see the intramembranous bones forming, right? That's the thing that's forming between those layers of connective tissue. And those tissues are like unspecialized at the time. And there's certain signals that happen that like tell the cells, hey, start building bone around that. The bones we are seeing down like in the arms, right, in the hands, those are formed from that hyaline cartilage models, because that cartilage exists there first, and then those bones can like gradually replace that with harder bone tissue. So when we are looking at bones of somebody who is already born, right, or postnatal, this is how bones are formed from after birth all the way up until you stop growing. For a lot of us, that's around age 25. For me, probably 12. That's a short joke for y'all. And here's really what's going on. We're seeing that epiphyseal plate in long bones. So that was that spot in between like the shaft of the bone and the end of the bone. When we are younger, that plate is made of cartilage, that hyaline cartilage. And this is exactly how the bones grow. This is the spot from where they're growing. So at the end of, or when we start growing up until the end of growth, that cartilage is getting replaced by bone, and that cartilage is kind of moving along longer and longer and longer. We'll look at a diagram too to see what that exactly looks like. At the end of growing, that cartilage is totally replaced by bone. So that like growth plate is no longer actively growing, right? So that once that cartilage is replaced by bone, hey, we're done growing. Done growing. The blood vessels in our body and osteoblasts, so those bone builders, are surrounding that cartilage. And as it disintegrates, they're building that extracellular matrix, so full of all that good calcium. Calcium and salts are deposited in that matrix. We call that calcification, right? And that's what like makes our bones like very like sturdy, strong, hard to break. If you've gone to the doctor for a physical, doctors can predict our growth from x-rays of those growth plates. As soon as it's fully calcified, though, you're done growing, right? So calcified, we're done growing. They call that an epiphyseal line. And then if you are still growing and that plate gets damaged, growth could permanently stop in that specific bone, or it could grow unevenly. It really depends on the extent of the injury. All right, so here we're seeing, I kind of diagrammed this out. The red spot I've got here, we're talking about like growth just in the fetus, right? So like everything A through B through C through D, right? This whole part is like how we're seeing bone growth happen in a fetus, right? It starts out just as like this cartilage that we're seeing. We saw that stained like on the next thing. That gets replaced by bone eventually, and you can see it getting replaced like on these edges here, right? So as that calcifies, right, that's what's going to turn into bones. We're building those bone cells and that extracellular matrix around here. The more we can get included in this, the more like durable those bones are going to be. And finally, you can see like this one is going to be super similar looking to those other ones. So we're seeing like still a lot of cartilage like here, 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 right? That's going to be what allows somebody to keep growing. But we're getting it replaced by bone, so it's not like as fragile. In the second area, we can see like this is how a child is going to grow. So if we're looking at this plate right here, what we call like a growth plate, right, that's still cartilage. So that cartilage is what's going to allow bones to like get built around it. As long as that cartilage is still there, those bones can still grow longer and longer. And then finally, what we're looking at on the other end, hey, this is like an adult growth is done. You can see that like there is kind of a faint line of where those growth plates used to be cartilage. And this one's even harder to see up here. But it's no longer cartilage. So once it's replaced by bone, we're done growing there. But you can still see like where it used to be, where those growth plates used to be. The one thing that we should make note of is you can see as a fetus, right, there's no space in between here, but we start getting that medullary cavity going on here, which is super important for nutrient transportation as we grow older. It's also where we're going to store some like marrow, which is important. So we need those osteoclasts to also continuously be making that medullary cavity longer and longer. I'm struggling to circle that one. And finally, what happens when we break a bone? So what happens if there is, you know, a collision, for example, the bone breaks, we call that a fracture. If the bone breaks and breaks through the skin and has been exposed to this outside world, we refer to that as a compound fracture. There's many ways that this can happen, like a bone breaking. It can be a traumatic thing, right? Like something really happening to you. It can be a spontaneous, where it just like shows up one day, or it can be like a pathologic, like there's something going on like physiologically that's changed the structure of our bones and therefore they're breaking. So if we look at this example here, we can see that Silas has a fracture. I'm going to assume from football or wrestling. But right here in his hand, if we were going to compare this fracture to other fractures, and you were going to describe this to people, would you say that this is a normal fracture or a compound fracture? So remember that, hey, a compound, if you think that that break in his bone probably broke through the skin and has been exposed to the outside world, then it's probably compound. If you're saying, like, no way, it's too small, right, then we're just going to classify that as a fracture. It didn't come out of the skin. So you think about that, discuss it with someone around you, see if they're thinking the exact same thing. So what's happening when a bone does fracture? So if you're somebody who's broken a bone in your hand before, maybe in some other way, here's what's going on. When that bone breaks, you're going to see a lot of vessels in that bone break as well. So we can see that on the image here, right? As soon as the fracture occurs, these vessels in here, right, they are also broken open. The outer lining of the bone, the periosteum, also probably tears. When we see this happen, we're seeing like, hey, there's a lot of blood going on because those vessels broke. This is called a hematoma, when the blood spreads across that damaged area. This will cause vessels to dilate or get bigger. Tissues might swell, things might get inflamed in that area, and that's all really to promote healing. Once we see like, hey, we've got some of this, it's not like full of fresh blood anymore, right? We're starting to like have the blood vessels have like clotted, right? It's not fresh. We're going to see some osteoblasts come into that area. That's right here. And those blasts, right, they're going to build a new bone. So we see the osteoblasts. They're going to build new bone where it's been broken. There's going to be a bunch of them. They're going to divide and multiply. They're going to be near this area where we've had the break happen. They're building spongy bone all around that. We get some tissue that also develops around here, which is going to promote healing. And then some phagocytic cells are going to remove the blood clot, which is my favorite part. They're saying, we got to get this out of here. This isn't like really great. So they're going to take a lot of this part away, right? We want to get rid of that blood clot and just have bone there. So you can see from like figure B to figure C, hey, we've got like way less of that stuff going on. Any cells that were damaged in this process, they also are removed from this spot. And this is when those osteoclasts appear. They're going to crush some of those bone cells. So if there's any bone fragments floating around, right, we don't want that. We don't want bone fragments getting in the way. They're going to reabsorb some of that or like dissolve it so it doesn't damage us at all. And then any gaps between the ends of the broken bone are going to be filled with this fibrocartilage, which can then get replaced by bone cells later. Usually, if this happens, you can still see like, hey, this area might look a little different, right? We've got like maybe a larger spot over here. But for the most part, this is like pretty much perfect, right? We can walk again. We can do whatever we need to do again. Maybe on an x-ray, you can tell that that was broken. But for the most part, this is like a strong bone that can function normally. All right, the last thing you are doing, we will probably do this tomorrow together. You're going to get a little check your understanding of how do we classify bones. So you'll get some bones that you'll cut out of a sheet. You have to piece them together accurately. What I mean by this is do not put a leg bone where the arm should be. Make sure the arm is consisted of arm bones. Make sure the bones are facing the right way. Do not put a femur sticking out the wrong way. Then it can't connect to that hip really nicely. Once you have decided that your skeleton is accurate, glue that baby together, and you're going to create a code based on what types of bones are on your skeleton. So you should be coloring the long bones are going to be all one color. You can decide, but if you decide it's red, all long bones need to be red. Don't color one femur red and another femur purple. That's silly. All the short bones should be another color. The sesamoid bones are a different color. Irregular bones are a different color. Flat bones are a different color. What I want to see on your sheet is like a nice little key off to the side somewhere. So that way I know that you know what's up. And hey, here's a bonus. Make your skeleton doing something fun. If you're a super awesome tennis player, maybe your skeleton's going to be playing tennis. Maybe you wish you were a super awesome tennis player. Your skeleton could still be a super awesome tennis player. And then finally, your last thing, if you are somebody that you are feeling like you learned a lot, you're ready to answer like the little summary of your notes. Hey, you're going to circle back to that essential question. How does this entire system support, protect, keep humans functional, right? One big thing that I would love to see us all connect this back to is how do we stay balanced, right? So how do we maintain homeostasis in the skeletal system? If you can answer that after this, you are super ready for any question I throw at you on your skeletal system test. So you're paying attention, you're doing great. Nice job. I'll see you real soon.